So let's look then at the grand finale, path modeling and SEM. We'll see how far into this we get. I've got a lot of stuff here. Normally I like to spend 2 weeks on this, but we got a little bit compressed, so we'll do what we can do. So this is lecture 9. Let me switch gears here in the recording. Okay. So some folks have had path modeling before and some folks have not. In my worldview, if I ran the world, path models would be taught right alongside regression. You would not have to take an SEM class to learn about path models, because path models are no different than regression. It's just a series of relationships among observed variables where you get to have more than one outcome operating at a time. So that's why I don't do path models in this class, because this class is about latent variable measurement, which is the SEM side. But the syntax of path models is exactly what the SEM syntax is going to look like, and so therefore I want to make sure that you've at least seen that so that you can know that the models to describe relationships between variables, the syntax is the same, whether those variables are observed, boxes, or latent circles. Building the latent circles is the tricky part. So first off, here's some path model vocabulary that I typically don't bother with here. These are pictures first. Vocabulary is coming next. So here on the right here, this is an example of a path model. I have 2 observed predictors, x1 and x2. I have 2 outcomes, y1 and y2. In this case, arrows that are directed. The thing that it's going from is the predictor, and the thing it's going to is the outcome. In this case, we can say that we have y1 is partially caused by these other variables, no, caused, predicted by, and it has variance left over. So this idea that a variable has an estimated variance is sometimes depicted with a latent circle out to the side, and sometimes it has a directional arrow into itself. Both of those things mean variance in this notation. If I wanted to write a linear model that describes this path diagram, it would look like this. I have a regression model for y1. I have a regression model for y2. I'm using superscripts to keep track of which beta and which error term goes with which outcome, but otherwise this is regression. So I could fit this type of model in any structural equation modeling package, or what I would call a multivariate relationship package, or I could actually fit it in proc mixed. You can do multivariate analysis in mixed model packages because you can tell it that y1 and y2 come from the same person, they each get their own variance, and they get a covariance. So these models have nothing to do with the rest of this class, nothing at all. Why do multivariate models? There's a couple of specific types of research questions that you have to have both outcomes in the same model to be able to answer. One is differences in effect size. So does x1 have a bigger effect on y1 than it has on y2? Those types of questions, you have to have y1 and y2 in the same model. And this type of framework has a special name in the context of dyadic data. It's called the actor-partner interdependence model. Doesn't that sound fancy? That's my notation for it is this, the actor-partner model. So if you think of x1 as person A and x2 goes with person B and y1 goes with person A and y2 goes with person B. These could be mothers and children, right? They could be spouses, partners, caregivers and patients, 2 people who are together and for some reason or another. And so the x1 to y1 and the x2 to y2 are known as actor effects. It's my x on my y, but then how my x affects your y, those are the middle parts. Those are the partner effects. And so if you want to know if my predictor predicts me to a greater extent than it predicts you, that is testable by setting these fixed effects to be equal to each other in whatever pattern you're trying to ascertain, and seeing how much worse the model fits. So that's a special case of what I would call multivariate regression, broadly construed. Multivariate means more than one outcome at a time. We also need to do more than one outcome in the same model to test indirect effects in terms of mediation. So just as we learned in any latent variable measurement model, there's two kinds of solutions you get back, standardized and unstandardized. Same deal. Unstandardized predicts covariances between variables. Standardized predicts correlations. You know all this already. Here's some more words. Exogenous versus endogenous. We took a vote last time and decided we're not going to use those words. Exogenous, I think of as the X, that means predictor. Endogenous, meaning the arrows are going into it. That's why. So you can either say IVDV, predictor outcome, exogenous, endogenous, X and Y. That's terminology that you will see in these. In this case, down here, Y1 is both an outcome with respect to X1, and it is a predictor of Y2. It's still considered endogenous. It would still have a residual variance because it's being predicted there. All right, missing data. How many of you have heard that structural equation models handle missing data? Or FIML handles it. It's done, fixed, problem solved, right? No one's ever tried to tell you this? Good. Then let me be the first. It doesn't. It's not magic. So this is where the intersection of missing data, type of variable in the model, and software comes into play. So what goes into the likelihood? Outcomes only. So if you're running M+, for instance, and you have a predictor. So let me give you the context of a model here. X1 and X2. In these models, these are predictors. If you fit this model, in which you tell M+ to estimate all of these regression paths, the syntax is pretty straightforward. As we'll see, it's Y1 on X1, where we regress Y on X. Y2 on X2, Y2 on X1, and Y1 on X2. Cool. M+ then automatically will estimate intercepts for Y1 and Y2, and it will estimate residual variances. In other words, you get a picture here. You're specifying these series of equations. If you reference this beta and these four betas in the middle, it knows that you must also need intercepts for each variable, and then you must also need variances left over, residual variances. Cool. But what does it do with respect to X1 and X2? Nothing. They're not in the likelihood. All we need to know is what their values are so that we can calculate what the variance left over should be. So if you have predictors that are treated as predictors, meaning you don't do anything special, you cannot have missing data on them. M+ will kick them out. They're not handled. They're deleted.
The people with missing data, not the whole variable.
The people, the rows. Yep. Because it needs to know what the predicted Y would be for each person, and it can't figure that out if it doesn't have the X. Gone. So where does this idea that missing data get handled come from? If you trick it. If you bring the predictors into the likelihood, that means you trick the program into thinking they're an outcome. Even though they're not being predicted by anything, if you refer to some aspect of their distribution, their mean, their variance, or their covariance, now they're outcomes. They're in the likelihood. That means you assume missing at random, and you can have people with incomplete data on those predictors. Sounds cool, right? However, whenever you have something in the likelihood form is based on some sort of distribution. In CFA, what's my distribution for my items? Multivariate normal. In IRT, what's the distribution for my items? By Bernoulli for binary, or how about categorical more generally? Multinomial. Yeah, there's some kind of distribution that goes with the likelihood function. So in order to stick a predictor in there, you're saying it has that distribution too. So if I have a 2-category grouping variable that I forgot to measure for some people, and I want to put that in my likelihood, I would assume that that 2-category variable is multivariate normally distributed. Not so much. So yes, missing data is handled to the extent that you are allowed to put it in a distribution and make a distributional assumption when you put it in the likelihood. And this is where the intersection of software and textbooks to me is really interesting. So when I was learning SEM, the books that were published in that era, which would have been the early 2000s, they all said things like, all the variables have to be normal, all of them. SEM assumes multivariate normality. Because at the time, the software packages didn't have this option to put predictors in or out of the likelihood. Anything in the model was in the likelihood. So of course, anything in the model had to be multivariate normal. But what do you do if you have, say, a treatment study, and one of the variables you need in your model is control versus treatment? Does that mean you can't put it in a structural equation model? No. It just means you can't use that software package that does it that way. Now, what that software package is, as I have learned, is most of them. Proc, Calis, and SAS, everything is in the likelihood. There is a version of Stata. The SEM package, I believe everything is in the likelihood, but GSEM, it's supposed to have the option. So this is something to pay attention to when you're looking at different software packages, whether or not you're allowed to have predictors be part of the likelihood or not as an option. Whenever you have predictors in M+, and you reference their mean, variance, or covariance, you're putting them in the likelihood. So the intersection then of what to do with missing predictors, this is where imputation sometimes comes into play. Imputation also requires you to specify a distribution for your predictor. So it's just as important to pay attention to that when you're trying to bring it into the likelihood in these models, as well as when you're trying to create multiply imputed data sets. So pay attention to this in terms of how you specify your model. All right, so fit. We did all of this before. Under-identified, just-identified, over-identified. In the context of a path model, fit is rarely that informative because you don't have that many degrees of freedom left over. Path models, I generally tend to strive for just-identified models because they can't be wrong. I put all the paths in and see what is related to what. So for example, each of these pictures would have 1 degree of freedom, because the path that I've omitted is the direct effect from x1 to y2, whether it's an arrow one-headed or two-headed. These would be just identified path models where all possible paths are estimated. That way you can describe the relationships fully and perfectly. You can't do something like this down here. You have 1 covariance, you can't get 2 paths out of it. But model fit, all that stuff you did before is the same. Effect sizes and significance. Here's a question that I get more often than I would like. A model that looks like this with coefficients on that order, this model has 2 degrees of freedom because it doesn't have a relationship between y1 and y2, and it doesn't have a relationship between x1 and x2. So it might fit really, really well. So how can it be that I may have non-significant paths for everything and still have it fit really, really well. What's fit mean?
You're reproducing a pattern, doesn't have to be a significant pattern.
Yep, we're reproducing a pattern. The model accurately mimics whatever relationships are there in the data. Says nothing about if there are any relationships to bother with. Think about a single regression model, the things that you would have done your very first stats classes. Did anyone ever talk to you about over-identified, under-identified, just identified in regression? No, all regression models are. Question? No, you're not going to volunteer? Okay, let me finish my sentence and then it will be your turn. All regression models are just identified. Fit's not a thing. If you're predicting one outcome, you have its intercept and its residual variance. It's perfect! Hooray! No, what matters in regression? Effect size, R-square, standardized coefficients. That's not the same thing. Now your question.
If your variables don't have any relationships with each other, would you always get a good model fit?
Mm-hmm.
Because it would just mimic again the non-relationship.
Yeah, so at the extreme, if these four variables are completely uncorrelated, you could fit a model with just like 4 boxes floating in space and no relationships among them of any kind, and it would fit really well because your boxes floating in space have accurately captured the zero correlation matrix they came from. Yes, they have to do this. Yeah. So that's why I don't care about fit in path models. Like, I don't even pay attention. I would just go ahead and put the missing stuff in there, and then I know that whatever pattern I have is the right one. I have created, perfectly recreated whatever pattern is to be had in the data, because most of the time when you're fitting these things, the end question is not does it fit, but does X1 predict Y1? Does X2 predict Y1 after controlling for X1? Those are the kinds of questions. They're almost always about the paths. Good fit is a prerequisite to looking at the paths, but good fit really doesn't mean much in this case. It means a lot more in the context of measurement models, where the existence of having loadings that perfectly reproduce covariances is a theoretical statement about whether your items are measuring one thing or more than one thing. So, yes, effect size. And your output will give you unstandardized versions of these, standardized versions of these, as well as R-square for Y1 and for Y2. You'll get all of that in one shot. Other questions? Okay, terminology. Mediation and moderation. Do you guys know the difference? Good. Don't ever screw this up. Mediators. That's the top one. Could I have something like age be a mediator? What causes age, which then in turn causes something else? Birth date, yes. That path better be one, or something went awry. Yeah, no, be suspicious when you hear the word mediator and then you hear personal characteristics. Those are moderators. Unless your model says this caused your age, or this caused your race, or this caused your gender, or this caused your grade, or anything else, nope, those are moderators. Moderator is a term that gets used differently depending on which field you're in and which grant you're applying to. So IES insists that everyone have mediators and moderators as part of their hypotheses. I don't think they mean moderators. I think they mean predictors. That's my own hypothesis, and when you look at their language. So you'll also sometimes see pictures like this middle one here, where the box predicts a line. That's not a model. That is like a representation or a conceptual illustration. That is not a model. What that model actually would look like is down here. The idea that the relationship between x and y depends on m is captured by an x by m interaction term. So when I think moderation, I think interaction term. But in some worlds, you might actually think of m and x as moderators too, because they moderate y. So mediation stuff, I have an example of that for you. It would be remiss if I didn't cover it at least a little bit. To me, mediation is nothing more than regression with a better marketing campaign, but it's a big deal in a lot of fields, so I want to make sure that we at least hit it. So the whole idea of mediation is, does x predict y differently before or after you control for m? That's it. So the relationship before you control for m is labeled as C in these. This is the terminology that's used almost exclusively. And then the relationship from x to y after controlling for m is C prime. The new C, the adjusted C. And the extent to which C and C prime differ is the test of mediation. So a long time ago, somebody figured out that the difference between C and C prime is algebraically equivalent to the test of whether A times B is different than 0. So nowadays, when people want to talk about mediation, it is almost always done in this A times B way, which is known as an indirect effect. So you may have been taught mediation in your regression class. Did anybody do this? Yeah. And you did it like in SPSS or something in chunks? Yeah. So if you needed to do this in software where you can only look at one outcome at a time, you'd run a model of x predicting m, you'd run another model with x predicting y, and then a third model with x predicting y and m predicting y, and that would give you these things, and then you can throw it into some kind of macro that someone wrote for you to get the right math to do the test of the indirect coefficient. Or you could throw these things all in one model and save yourself some time. So whether A times B is not different than 0 is the question. Here's some stuff on here. C doesn't have to be significant to play this game. The question is whether C and C prime are different. So more positive, less positive, more negative, less negative. Even if one or the other is significant or not, that significance doesn't really matter. People argue all the time about the best way to do this. Bootstrapping, multivariate, delta, blah, 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 blah. I just can't care. I'm sorry. The research is all here for you, so you can go look it up. I just can't care. I've never seen it matter in real data. Here's an example, though, that I can show you if you want to know how to do something like this. And this is a published example. A former colleague of mine at Nebraska wanted some help. She initially had written a paper looking at all 5 of those boxes in the middle and on the right in separate regression models. It was a very long paper. And the reviewers came back and said, can you just put these all in one model, because I don't want to read this all. And so she said, can we do this in one model? And I said, sure. And so we did it, and she let me use it as a class example, for which I am very grateful. But this is the kind of model that you would be hard-pressed to duplicate in a single regression framework. She has 4 different mediators, and she's interested in differential, unique mediation after controlling for the other mediators. So this is a social psych type of data set where we have scales. So we're adding shit up to form composites and all of these things. Mindfulness, and then 4 mediators here for various forms of sexism or motivation to avoid it. And then this is a thermometer rating as to how warm people feel towards feminists. And the idea is that the extent to which mindfulness relates to this outcome should go through these 4 mediators. So let's take a look. Because the syntax is exactly what we will need to do the same type of analysis with latent variables. So 653 undergraduates, men and women. Ended up using a multiple group model to examine the extent to which mediation differed by gender, but we can start with a single group model. So here's the data that matter. Table 3 from the original paper, where the data below the diagonal are the women. The data above the diagonal are the men. Those are my correlations. The correlations among these 6 variables, that's what I'm trying to account for in my path model. The diagram itself doesn't show relationships among the middle variables, but as noted in a footnote, I have all possible covariances among the middle, so the model is just identified. So here's what the code would look like to do this. So on the name statement, the 6 variables that are part of my story here, missing data code, I centered mindfulness because all predictors need to have a meaningful 0. That doesn't change in this world. Ended up creating a new outcome that was an average of 2 other things to address some other reviewer complement or constraint. We ended up using bootstrap standard errors for the indirect effects so that we wouldn't get yelled at by somebody who cares. And here's the model. So when I write code for this, I almost always draw a picture and then write the code that goes with the picture. It's really hard to make sure you don't miss anything unless you have a working diagram. M+ actually will draw diagrams for you. There's an option for it, but you have to have the right form of Java installed, and these computers do not have that. But the first line there under model, bring X into the likelihood. So mindfulness is the variable that was on the left by itself. That's a predictor. A few people did not have data for mindfulness, and we wanted to keep them in the model. Since mindfulness was normally distributed, or approximately thereof, I went ahead and brought it into the likelihood by listing it in brackets. That refers to its intercept, and listing it just by itself, that refers to its variance. So I have labeled all of my parameters here so that you can keep track of what these things mean. The labels are not strictly necessary for anything other than the direct effects that we're going to use to form indirect effects. Same thing here. These are the other 5 variables. When I put it in brackets, I'm referring to their intercepts. When I list them by themselves, those are their residual variances. So that's these 4 in the middle and the y there. Then we go into each piece of the model. So the X to Y relationship, as I have labeled it here, is non-trad on mind1C. So on creates the directed arrow where it's Y on X. Now that is backwards from how I always think about it. So you can see my own notes above that. Direct mindfulness predicts non-trad. So I write it as X arrow Y, but M+ insists that you do Y on X. Why? Job security. Other programs let you go back and forth. Like Stata lets you go either way. I think R lets you go either way. But just think of it as on is an equal sign. So if you were going to write out a model, it's always Y equals and then the rest of the stuff, right? It's never stuff equals Y. No one ever starts with the outcome on the right side. It's always on the left. So think of it this way. Equals is on. So Y equals X. That's the first line there. Then I've got the middle part of the model here, the left side. This is X to each of my mediators. Here's the right side. Here's the mediators to the outcome. And then here's all possible covariances among the mediator variables. That's it. Now you know all 3 of the major commands in M+. You learned by, that's for latent variables, right? Measured by. With, you already knew, which is covary. And now you know on. That's it. Now you can do structural equation modeling. It's anticlimactic, isn't it? Now, why fit these models in M+? Here is the benefit of doing so. Model constraint we have used for several things this semester. Model constraint we use to calculate omega. Remember? Do math. We can also use it to calculate indirect effects. So each of these 4 lines here is an A by B, where the A path is the X to M, and the B path is the M to Y. So I have labeled, for instance, this path X to M1 to Y. That new parameter is my indirect effect. So I can get all of the information that I would want to know out of these relationships in one model. Pretty cool. Here's my fit. Look at that! Do I win? It's more like I never tried to play. But yes, in the original version of the paper, at no point did I talk about fit. And this is why. And then, of course, reviewer 3 is like, if you did structural equation modeling, you need to report fit. Okay. My response, dear reviewer 3, who'd like to help me? Dear reviewer 3. This model is just identified. Now, what if reviewer 3 doesn't know what that means? Let's break it down. Don't say covariance matrix. Reviewer 3 doesn't know what that means either. Hey, I like that. I can't add any more lines. Yes. I have put in every possible relationship that there could be. I know that because right here, 0 degrees of freedom. I can't put in any more lines. I like that. So yeah, I can't be wrong. Now, I shouldn't get super excited like I made this model fit. There's no chance that it can't fit, because I used every possible means by which there would be to fit it. That's like if I said, can I get change for a $5 bill? And then you handed me 5 ones, and I'm like, woohoo, I got 5 ones! It's like that. It's the same. Yeah.
I guess I'm not understanding how this is different than path analysis and why this counts as structural equation modeling. There are no variables.
You are correct. So this is how I knew that reviewer 3 would not understand just identified or covariance matrix, because they thought I did structural equation modeling. This is not a structural equation model. This is a path model. There's no latent variables here. Now, the question that they should have asked, and I'm really fortunate that no one did, too late, it's published. These are all subscales. Quiz question. What's the question? Come on, be reviewer 3, folks. Yeah, Betsy? How do I know I'm measuring one thing? Yeah. What am I assuming and adding shit up here? This is what I call the ASU measurement model. Not to be confused with Arizona State. ASU stands for add shit up. Each item is equally discriminating. More formally, it's parallel items, I'm assuming, that they all have equal loadings and equal error variances. That's the only situation in which my factor score and my sum score would be perfectly 100% correlated. I'm assuming dimensionality, right, that there's only one way to be hostily sexist across these items. Yeah. So yeah, that's the question that I'm really glad no one asked, is why isn't this a structural equation model? I had 600 and some odd people. The real reason is because this was already a revise and resubmit when the person came to me and we didn't want to fix what wasn't broken when you're pre-tenure. But yeah, this could have been a structural equation model. So if this were my data now, like if this was going to be your dissertation, I would insist that each of these boxes be verified. At a minimum, Do your homework to make sure that this is in fact one scale. If you want to add shit up, you should demonstrate that either tau equivalent or parallel items holds. Otherwise, this is all suspect. Yeah.
Why is this different than the mediation models where you just add in the mediator as like a controlling for the mediator?
Because there's 4 mediators.
You can just add in 4 predictors.
Yeah. I could have had a whole lot of stuff here, but this was the only things that were relevant to the story that this person was interested in.
I guess, I mean, what makes it just different from just a normal regression where you have 5 predictors, motivation, internal, external, mindfulness,
Because it's fancy. Because it's mediation, damn it. That's why.
Okay, but you would say that this is
No.
the same.
No, this is they want to know if X predicts Y after controlling for some other stuff. That's regression. Yeah, question?
I'm wondering if maybe one of the benefits of doing something like this and like an SEM type model, or what I know it's not really.
Framework. You can say framework. It's an SEM framework.
Is that like in regression, if you run more than one regression, you've got to, if you're doing like a box routing adjustment technique, you've got to make the p-value significantly smaller and smaller and smaller because of all these other theoretical reasons. But if you run all your models simultaneously, you don't have to like correct or
Yes.
that stuff. Right? Is that like a reason why people do this?
It is a false reason because 1 in 20 p-values is still wrong. That problem doesn't go away, but people are not going to yell at you about it. If it's one model, even if this one model holds the information from 5 different regression models. So yeah, I don't see that as solving type 1 error. It depends. So if it's in a regression framework, people are less likely to have a problem than if you had a multiple group variable as a predictor and you reported an omnibus ANOVA and then pairwise follow-ups. Then you'll get slapped with the p-value thing. But to me, it's not different. 1 in 20, right? Whether they're provided by default, whether they come from separate models or the same model, it's 1 in 20. So, yeah.
The only thing that this one would provide that's above and beyond to the normal regression would be 5 predictors would be these left 4 paths, right? The mindfulness to the mediator. So we get those loadings and we wouldn't, or the covariances and we wouldn't ordinarily.
We get the paths. So I would call these regression slopes. But yeah. So this is why the original version of her paper was so long. She had to report a regression from mindfulness to M1, mindfulness to M2, mindfulness to, actually she just needed correlations, but gender was part of the story at that point too. So yeah, why do this? To the extent that you have multiple outcomes that are correlated and missing data, it's supposed to work better because they can borrow information across outcomes to have them all in the same model. To get indirect effects that you can then bootstrap so that no one will yell at you about using the wrong test of your indirect effect. And also, the second half of the story, which is foreshadowed by this correlation matrix, a multiple group model. So what we ended up doing, which you already know how to do now, there, multiple group path model. Is the extent of mediation different between men and women? That's a much more complicated question to answer in piecewise regressions. So, but you know how to do it. How do you test any kind of multiple group differences? Constrain the thing, see if model fits, worse. So I tested direct effects and indirect effects through this method here. And there's no words because they're all in the original paper. You can go read it. I helped write it. I stand by it. So, ta-da! Path models. Questions? So now if we take these things right here and turn them into latent variables instead, it looks exactly the same in terms of syntax. We're ready to do SEM in an SEM framework. Yeah. Question? In this case, so this model is everything estimated separately. Then in subsequent models, you constrain each of the paths and watch the change in fit. So for instance, if I wanted to test gender differences in the indirect effect from X to M1 to Y, then I end up with the same, let's see here. This one is the difference. We can do it that way. So this one is testing the differences in the paths directly. This one down here uses the syntax version that you know. So if I label X to M1 the same in both models, and then I label the M1 to Y the same in both models, that's 2 degrees of freedom, constraining those paths. And then the model no longer fits perfectly. Conveniently, if you already start with a perfect model, when you do these constraints, that's my likelihood difference. It does it for you. 2 degrees of freedom is what you get when you make A and B the same across groups. So we are out of time, but I'm happy to answer more questions. We will finish everything next time. So please finish your last quiz, and I will see you on Wednesday. Office hours start now.